My name is Kamen Kozarev, and I'm a researcher at the Harvard-Smithsonian Center for Astrophysics. So let's talk a little bit about the interplanetary propagation of these particles. What happens when they're created, let's say, near the sun, and then they start moving out into the solar system. I'm not going to go into too much detail because it gets very technical very quickly, but I'll try to just introduce the terminology for these different types of processes that influence the interplanetary propagation. There are different types of transport of the energetic particles. You have spatial diffusion, that is movement, physical movement in space. You have a pitch angle diffusion, which is the orientation of these distributions of particles to the overall magnetic field that they experience. So in other words, they can be gyrating around the magnetic field, moving along it in the opposite direction or somewhere in between, and this is called pitch angle diffusion. You can also have diffusion in momentum space. In other words, they can change their velocities and energies. You can have an interaction between magnetohydrodynamic waves and these particles from which they can gain or lose energy. They can be influenced by electromagnetic waves. What we try to do with observations is we try to fit a model for the propagation and transport of these particles, and from that determine the diffusion coefficients, the coefficients that contain basically all the physics of how these particles moved around the solar system. So let's talk briefly about spatial diffusion. What it is a superposition of many small, statistically distributed changes in the direction of propagation. You can think about a pool table, a billiard table, where if you hit one ball, it will hit another ball, it'll change its trajectory, then it'll hit a third ball, change its trajectory or direction again, and so on and so forth. For this, since we're talking about these very small changes in the movement of each individual particle, but there are many of them, it's not very useful to use a single particle approach. It's better to use ensembles of particles and try to determine their average behavior. So an example of this, of spatial diffusion, might be a drop of ink in water, or when, for example, when you pour some milk in your hot coffee, you can see how immediately it starts to spread around in a larger and larger, trying to basically taking over the whole available space. So this is what spatial diffusion is. Another type of spatial diffusion is Brownian motion, these particles that move randomly about the air. To illustrate the point of spatial diffusion, we can talk about one-dimensional motion. So on the top graph, you can see an example where you have a particle that moves around bouncing off of other particles. And you can see how over time, if you have many of these interactions, it moves around its starting position of zero displacement. And these interactions are kind of random in nature. So it may go in one direction, then come back, then go and come back. So it's moving on average just a little bit, okay? And each interaction equals a motion by a plus lambda or a minus lambda, and we'll talk about what lambda is, but it's a certain distance. If you do this many times, and if everything is random, in other words, if the motions are random, if the particles are randomly distributed, you would expect that the particle, after a whole bunch of interactions, would be back where it started, because everything's supposed to be random, and you can't choose a certain direction. There is no reason to have a certain direction along which the particle will advance. However, when you look at kind of real observations in real life, which is the bottom plot, you can see that there are substantial excursions from the 0 point. So this randomness concept is true when you have really very large numbers of interactions. To describe this better, we use a characteristic statistical quantity, which is the average squared distance. It's basically a summation of the individual displacements of the particles over time squared. And it gives you a good idea about how much the particle actually moved from its origin over time. I'm not going to go into the details very much here, but what's most important to remember are these diffusion coefficients, which are at the bottom of the page, and they just tell you how much these particles have moved. And they include in them the velocity of the particles and lambda. What lambda is what's called the mean free path. Okay, so that's the average distance between collisions, successive collisions of the particles. So there are different types of diffusion based on the initial input of energy. When the particles are released near the sun, so you can see on the right side here, you have a plot of the intensity over time for different types of lambda, mean free path. So when you have a large mean free path, that means that it takes a long time or a long distance between the particle collisions or interactions. And then what you observe is this peak, which is very sharp at the beginning of the event, when particles have diffused, but not by much. So in other words, if you inject them with at a certain time, they will not interact with each other very much. And what that means is that they won't spread out in time. Okay, in other words, they won't exchange energy too much. Now, when you have a small mean free path, that means that there's a lot of interactions between the particles, and so they spread out in time and in space. Another type of motion is the so-called convection or diffusion convection. And what it is simply the motion of the particles with the fluid. In other words, the solar wind will carry the particles with it. And that's the so-called convection. Diffusion and convection, they can be described by a single equation, which is called appropriately the diffusion convection equation. A third type of transport process is called the diffusion in pitch angle. As I told you, there's this concept of gyration of the charged particles. First of all, let me just say that there are magnetic fields everywhere in the solar system. So whenever you have a charged particle, based on the physical laws, it will interact with a magnetic field that is present. And what happens is, if you have a magnetic field in a certain direction, a particle will circle around these magnetic field lines in a roughly perpendicular trajectory to the axis of the magnetic field. But it'll also move along the magnetic field. So you have two types of motion. You have a parallel motion and perpendicular motion. And pitch angle diffusion is simply the change of direction along the magnetic field that the particle can have. In other words, it can transfer some of this perpendicular motion of the gyration to the parallel motion. There's a quantity called pitch angle. So if you have a zero pitch angle, a particle will be moving exactly along the magnetic field. And if you have an 180-degree pitch angle, the charged particle, let's say a proton, will be moving in the opposite direction. Of course, all the other angles in between are also possible. In other words, it will transfer some of its parallel motion into the perpendicular motion. This happens, these changes between the different pitch angles really do happen to all these charged particles. Now, there's a problem that in space, when we talk about collisions, this is not really physically the bumping of two particles, such as in billiard balls, because the density is very, very low. So you don't really have collisions between particles themselves. What you have instead is these wave-particle interactions. In other words, you have the magnetic field acting like a whip moving around, And when it does, it can interact with the gyration of the particle under certain conditions, and it can bump it into one direction or the other. So that's what we mean when we talk about diffusion processes. It's really, and the interaction of the particles, it's not really the collisions themselves, but rather the interaction with the magnetic field imperfections. Analogously with the spatial diffusion of the particles, you here have pitch angle diffusions, which are these many small changes in the particle propagation in the pitch angle of the particles. And here you have a formula that tells you the pitch angle diffusion coefficient, where mu is the cosine of this pitch angle. And then you have an equation at the bottom that tells you how the particle distribution will change over time and space based on pitch angle diffusion. You can also have diffusion in momentum space. These magnetic waves that I talked about, these imperfections and perturbations that the particles experience when they move along the magnetic fields in free space, they can change its pitch angle, but also they can change its energy. They can bump it up in energy, or they can remove some of its energy, depending on the conditions. So as I said, the collisions between the particles can be neglected in free space because it's very close to a perfect vacuum. Instead, you have the scattering at electromagnetic waves, and these are the so-called wave-particle interactions. And I won't go into details. Let's just say that some of the magnetic field energy transfers to the particles and vice versa. So when we combine all of these different types of transport effects, we can write a big old equation that is the model of how these particles behave. And what we have to do then is we have to fit the solution of this model based on some input parameters to the observations that we have. And here you can see on this plot we have some observations. On the top are the intensities of the protons during an observed flare event, and they have been fitted with a model that takes a certain inner boundary, and it also takes a certain mean free path for the transport, for the propagation of these particles. And this mean free path corresponds to the spatial diffusion, basically. So the model can give you the mean free path and the injection. And so it gives you hints about the acceleration, or at least where and when the particles were released near the sun. And it also tells you something about the scattering properties of interplanetary space, or in other words, of the trajectory that the particle has taken between the onset of the flare and the spacecraft that observed the particles. So what people do usually is they take a bunch of these models, they change the parameters a little bit, and then try to do the fit, see how well the fit does, and then little by little they find the best possible fit that will describe the observations best, and from that they extract these parameters about the scattering properties in space. Let's talk about energetic particles and shocks. As I mentioned, there are different types of acceleration mechanisms related to shocks. We have the so-called diffusive shock acceleration. We also have this shock drift acceleration, or SDA. Finally, we have the stochastic acceleration, which is sort of a random acceleration process that's also related to shock waves. The issues with the acceleration of particles in shocks, as opposed to flares, is the efficiency, how much of the energy can be transferred to the particle populations, and also the evolution of the shock during its propagation in space. These shock waves occur in free space between the planetary environments. In shocks in the solar corona, the bow shocks of the planets, these interfaces between the solar wind and planetary environments, and also supernova remnants for the galactic cosmic rays. What is the idea of the shock drift acceleration? The acceleration happens at the front of this shock wave, where you have a sharp change in the direction of the magnetic field in the direction of motion of the plasma of the solar wind, and in the density between the so-called upstream and downstream regions. You can see on the right here a little schematic showing you the shock surface, which is this vertical black line. And then you can see how the magnetic field changes, how the velocity changes. And the acceleration takes the energy from this induction field, the electric field, which is the cross product of the velocity and the magnetic field. This electric field accelerates directly the particles. This field is parallel to the shock surface. And so what the particles do, they end up gaining energy as they drift, as they kind of surf the surface of this shock wave. And this so-called drift will be in opposite directions if you have a positive particle or a negative particle. What's good about this way of gaining energy is that the direction is such that the particle always gains energy. Here you can see, for example, some sample orbits. There are 3 scenarios here that are shown. On the left, you see a reflective scenario. The particle starts on the left side of the shock surface, which is the vertical dashed line. And you can see how it gyrates, it moves around, it reaches the shock, but it doesn't go through. Instead, it bounces back to the left and is reflected. In the middle case, you have a transmission of the particle downstream, where it starts again to the left of the shock surface, or in the upstream, and then it is slowly transmitted into the downstream. And the final case is where you have a particle that starts on the right and it gyrates, and over time it moves on the left side. Now, these plots also show you the change in energy. So the vertical axis shows you how much energy the particles have gained or lost. At the start, they have an energy of 1 because it's a ratio of the current energy to the initial energy. You see how the particle gains significant amount of energy. Even if it's just reflected, it basically surfs the shock wave, and then it escapes either upstream or downstream. The problem with this type of acceleration mechanism is it has a simple geometry, and that's great, and it's easy to compute, but the energy gain in every single interaction is very small. And also, the way it's done, it allows for the particles to escape from the shock front. Also, the scattering is very small, and so very few particles are scattered back towards the shock to be reaccelerated to gain additional amounts of energy. It's unlikely that acceleration to higher energies than 1 mega electron volt can occur in these types of acceleration. The next and most pervasive mechanism for accelerating particles is what's called diffusive shock acceleration. In the diffusive shock acceleration type mechanism, what happens is the particles gain momentum as they repeatedly cross the shock front, and they are scattered by imperfections in the magnetic field on both sides that move towards each other. On the right here, you see an illustration which shows 2 people on 2 cars that are moving towards each other, and they're bouncing a ball, a table tennis ball, from each other. As they move closer together, what happens is over time, the ball starts moving faster and faster and faster. In other words, it gains momentum, and ultimately it gains energy. This diffusive shock acceleration mechanism is very simple, but we think that it happens a lot in interplanetary shocks, and the particles can gain a lot of energy from it. The final mechanism for particle acceleration in shocks is stochastic acceleration, which is very similar to diffusive shock acceleration, so I won't go into many details about it, but it's again scattering between these centers, but the scattering directions are random. So in other words, you don't have these scattering centers that are moving towards each other. You can have some that are moving away from each other, so the particles will lose energy. You can have some that are moving towards each other, so they can gain energy. On average, you have a small positive gain of energy. usually in this process.